Good morning, class. Here's pre-calculus practice test number 2, module 2, covering chapters 3 and 4, chapter 3, polynomial and rational functions, part 2. Let f of x equals x over x minus 2, and we want to sketch a graph of f using technology to determine whether it's a one-to-one function. Class, bear in mind, by now we've done some examples. The assumption is you can do it by hand, okay? So to speed up the process, you can use the technology. Obviously, you graph it. And notice it obviously passes a vertical line test, becomes a function, passes a horizontal line test, becomes a one-to-one function. That's the idea, first and foremost. So it's very obvious as to what's going on. Now, notice we can draw the horizontal line, horizontal asymptote and the vertical asymptote. And obviously, the vertical asymptote x equals 2, horizontal asymptote, both of them, the top and the bottom, have degree 1. The coefficient of x is 1 at top and 1 at the bottom, so y equals 1. So those are the asymptotes. So it's a fairly fast and easy graph. So yes, it is a one-to-one function because it passes a horizontal line test. If it is a one-to-one function, find the inverse function, okay? And come up with a graph. Okay. So first and foremost, this function, we're going to call it y because it makes it easier to deal with. Then we're going to interchange x and y, meaning this becomes x, these two become y. And right here, we do have the inverse. However, we solve for y by cross product. So x times y minus 2 becomes xy minus 2x. Y times 1 becomes y. Because we are solving for y, we're going to move things around as follows. So we move this, and it becomes negative y, and this one becomes positive 2x on the right. We factor the y out, and we divide both sides by x minus 1, and we call it f inverse. So y, or f inverse of x, is 2x over x minus 1. So we graph it fairly fast, and I hope you see that you can come up with the asymptotes clearly. X equals 1 is the vertical asymptote. Notice y equals 1 was the horizontal asymptote. The horizontal asymptote, they both have degree 1. The coefficient of x is 2 here, it's 1 here, so y equals 2. So these are the asymptotes. And notice V is and horizontal asymptotes in the following manner. What has happened? Again, the vertical asymptote x equals 2 corresponds to the horizontal asymptote y equals 2 for the inverse function. The horizontal asymptote y equals 1 corresponds to the vertical asymptote for x equals 1 for its inverse. Okay? That's what I want you to notice. This is extremely important. So having said that, let's come up with the domain of f. We go back to the original function and we say, okay, x minus 2. If you set it equal to 0, x becomes 2, which means all real numbers except 2. You have to exclude that. The way you exclude that, you get minus infinity to 2, union 2 to infinity. Let me erase my work so it becomes clear. And you use parentheses around 2's, therefore you are excluding it. So that's the domain for the original function f. What is the domain of f inverse? Range of f inverse. Right away, the domain of f and range of f inverse are the same, so this becomes minus infinity to 2 union 2 to infinity. What is domain of f inverse? We go to this function, and we say, okay, x minus 1 equal to 0, x equals 1 must be excluded. So all real numbers except 1. How do we write that? Negative infinity, comma, 1 union 1 to infinity. What is range of f is the same as domain of f inverse. You just repeat that, and we're done. It's really that simple, everybody. So a quick recap. You're given a function. It's a rational function. You can easily graph it by finding the intercepts, asymptotes, maybe a couple more points. You have the graph. Because it's a one-to-one function, you can find the inverse by interchanging x and y and solving for y. You graph the inverse, and you notice the domain of one becomes range of the other and vice versa. The vertical asymptote for one corresponds to the horizontal asymptote for the other and vice versa. That's the synopsis of the concept, understanding inverse functions. Now, we want to solve the following inequality, graph the solution set, write it in interval notation. How do we do that? The process uses what we call a sign graph. So we have a number line from negative to positive infinity. It just shows from negative 10 to 10 here. And then you use that to figure out the answer for any inequality. Number one, you have to factor everything in the numerator and the denominator. The denominator is fine. The numerator, we want two numbers. The product is negative 18. The sum is negative 3. And that means positive 3, negative 6. That's the first thing. Then you set the top and the bottom equal to 0. If you set the top equal to 0, the values are negative 3, positive 6. If you put the bottom equal to 0 is negative 2. You put those three numbers on a number line in order from smallest to largest. And of course, from negative infinity, this is negative infinity to infinity. Okay, so these numbers, the smallest is negative 3, so here. The next one is negative 2 here. And the next one is positive 6 here. So we write it in this fashion. And we're going to call this f of x, everybody. So this function, let me erase my work again. This function, we're going to call it f of x. So x goes from negative to positive infinity. F of x at negative 3 is 0. At positive 6 is 0. At negative 2, the denominator is 0, which makes the expression undefined, UD. Okay. Now we use what we call test points. So that means in between, right here, for example, we choose -4. Between these two numbers, we would choose, let's say, negative 2.5. Between the two, the best and easiest number would be 0. And of course, here, for example, 7. Now, then you put that into the original function, either in this format or a factored form, and you figure out whether it becomes positive or negative. Now, it's important to know, if you look at the factored form, each one has an exponent which is odd, so they will alternate. Because they alternate, as a result of this, go with the easiest one, 0. If I put the 0 into the original one, is easier. I get -18/2, which is -9. I'm not interested in -9. I'm interested in the sign, negative. If this is negative, they will alternate, meaning positive here, negative here. Or you can actually check, okay? Now, if I want to check, for example, if I put 7 And it's easier to use this one, the factored form, instead of that. If I put 7 here, 7 plus 3 is 10. It's just positive. 7 minus 6, 1, positive. 7 plus 2, 9, positive. Positive times positive over positive is positive. And you can work on the rest of it. But understand, again, if the factored form, each factor has an exponent which is odd, then they will alternate. They will alternate in sign. That's important to understand, everybody. All right, now let's go back. What are we looking for? Greater than or equal to 0. So look for positive. So in this, as well as this, we're going to say from -3 to -2, union 6 to infinity. Is -3 included? Yes. Why? Because we have the equality, so bracket. -2 included? No. We have the equality. How come it's not? Because it makes the denominator 0. So parentheses, 6 is included. Of course, what about infinity? Always takes a parenthesis. So bracket -3, comma -2, parentheses, union bracket 6 to infinity. That's the final answer. What makes it even interesting, as far as the sign graph and the solution on a number line is concerned, from 6, so we locate 6 and a solid point or bracket to the right, between -3 and -2, -3 is included, -2 is not. So that's the final answer as far as the graph on a number line is concerned. What makes it even more interesting, if we had, instead of this, x plus 3 times x minus 6 times x plus 2, we would use exactly the same sign graph, except this would become 0. And therefore, the answer would be exactly the same, except this parentheses, all of them become brackets. Okay, so I hope everybody is okay with that. So that's the concept of a sign graph. The end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of a graph. F of x equals a sub n, x to the power of n, all the way to a sub 0. Ultimately looks like its leading term y equals a sub n, x to the power of n. Meaning, if the degree is even, if the leading coefficient is positive, it will look like y, or f of x equals x squared, the first and the second quadrant. A parabola that opens up, meaning when x goes to negative or positive infinity makes no difference. F of x or y goes also to the same, positive infinity in both cases. However, if the exponent even and the leading coefficient is negative, it looks like y equals minus x squared. In other words, the parabola that opens down. Here's the third and fourth quadrant, first and second quadrant. So when x goes to negative infinity or positive infinity makes no difference. In both cases, f of x go down to negative infinity. If the degree is odd, then it depends on a leading coefficient being positive or negative. If it's positive, looks like y or f of x equals x cubed, the first and the third quadrant. If the leading coefficient is negative, looks like y equals minus x cubed, the second and the fourth quadrant. In the first case, when it's positive, it means when x goes to negative infinity, so does y. Remember, f of x is y. And if it goes, so that means negative infinity. This is the third quadrant. If it goes to positive infinity, y goes to positive infinity also, the first quadrant. This one is the other way around. When x goes to negative infinity, y goes to positive infinity. When x goes to positive infinity, y goes to negative infinity. That's really the bottom line for every polynomial. So it depends on two things, the degree and the leading coefficient. The next thing that helps, this is helping with graphing. The next thing that helps with graphing, behavior near is 0, and it depends on the multiplicity. 0 is x minus a, and the multiplicity is m. That means it repeats m times. If I say x minus c squared, that means x minus c times x minus c. That's the meaning of it. If m is odd, the function f crosses the x-axis at c0, which we call it the 0 or the root of the x-intercept. If m is even, f does not cross the x-axis at c0. So look at this one. This represents the multiplicity. Multiplicity 1, 2, 3, at even it can't cross. The higher the multiplicity, for example, both of them cross, but this is higher. The flatter the curve is at the 0. Notice this crosses, it's flat here. The sum of the multiplicities is the degree of the polynomial function n. Okay. A number of zeros theorem. A function defined by a polynomial of degree n has at most n distinct, unique, complex zeros. So that's pretty straightforward. Let's look at a simple example. When I graph the following polynomial using the end behavior and behavior near an x-intercept, in short means find all the intercepts, if possible. Discuss the end behavior, have a rough sketch. If need be, you can always pick up a few more points. There's no need for that. So how do we find the intercept? It so happened for the x-intercepts, we notice we can factor. If we put these two together, we can take out the x squared. And if we put these two together, we can take the negative. The idea is that to have a common factor, in this case, the common factor becomes x minus 5. So x minus 5 times whatever is left. From this one, x squared is left. From this one, minus 1. As you know, a squared minus b squared is a minus b, a plus b. This is, again, I'm reminding you, a squared minus b squared is a plus b, a minus b in any order. And this is x squared minus 1 squared. So we write it in this fashion. Okay. So right away, we have the following, everybody. 5, 0, negative 1, 0, 1, 0. And look at the exponents. All of them have no exponent. That means the exponent is 1. That means the multiplicity is 1. So we write them as pairs, 5, 0, negative 1, 0, 1, 0. And we put them along the x-axis accordingly. So we have from left to right, negative 1, 0, 1, 0, 5, 0. Also, we can easily see the y-intercept. What would be the best course of action? Let me erase my work and show you. The best way is to look at this one, the constant. In other words, these are 0, right? 0, 5 is the y-intercept. All right, so we have all the intercepts. So far, so good. Now we are going to look at the end behavior to figure out what we want to do. Well, we go back to the original one. The leading term is x cubed, where n is 3 and a sub n is 1. More specifically, a sub n, let me just write this for you. A sub n in this case is a sub 3 because the exponent is 3, okay? So I want to make sure everybody understands. A sub 3, 1, positive. So what does it mean? It looks like x cubed. So the first and the second quadrant. So that means this one and this one. So roughly looks like this one hits this one, goes back up, hits this one, and down. Now, the only thing is we don't know whether this is the max or goes this way or over here. Maybe it looks like that. Maybe it looks like that. This we'll find through calculus, finding the peak, if you will. What happens here, we may not know that either. Okay, where does the turn happen? Using calculus, we'll have that information as of next course. So let me erase my work. So it as x goes, this means the end behavior. X goes to negative, therefore y goes to negative infinity. X goes to positive, therefore y goes to positive infinity. Looking like that, very straightforward. And we are done with that. Great. We want to graph the following polynomial, and of course, using the end behavior and the x-intercept. G of x is x minus 2 quantity squared times 2x plus 3. We want to see what happens here. Okay. All right. So first and foremost, we are going to come up with the intercepts, x-intercept. One of them is 2. One of them is negative 3/2, set it equal to 0. 2, comma 0, multiplicity 2. Negative, set this equal to 0. Negative 3/2, 0, multiplicity 1. So that's very straightforward. So let's locate them. So this is negative 1. So negative 3/2 is here, negative 1.5. 2 is here with the multiplicity 2. So we have those 2 points. And we're going to draw this double-sided, arrow. So it indicates, this is what we use in calculus. It indicates when it hits it, when the graph hits it, has to bounce back. If it comes from up here, bounces back up. If down here, bounces back down. That's really the meaning of that. What about the y-intercept? Well, let's put 0 here and see what we get. So if I put 0 here, I get minus 2 squared times 3. Minus 2 squared is positive 4 times 3 is 12. So 0, 12. So locate 0, 12. And so we have all the intercepts so far looks good. I'm going to erase my work and notice if I multiply these two, this is x squared, this is 2x, I get 2x cubed and a few more terms. Now, I'm not going to get the rest of them because I really don't need them, but you're more than welcome to write the rest of them, everybody, okay? Why do I not write the rest of them? This is the leading term. N is 3, a sub n more specifically, a sub 3 is 2, positive. Which means, again, we have the same behavior as before. It looks like x cubed. So really, the third quadrant and the first quadrant, x goes to negative, so does y, negative infinity. X goes to positive infinity, so does y. And it looks like that. And this is a better graph. So I hope you understand. It's very straightforward. If you want a more precise graph, you can always pick up a few more points. But this is good enough. Again, as far as this one is, we know the location. This one, we don't know the location, okay? Where does the peak occur? We come up with the answer in the next course. Now, what is the least possible degree of the polynomial? Write an equation for the polynomial graph. So let's discuss a few theorems. turning points, peaks and valleys, local mean, local max, local mean, where the graph of a function changes from increasing to decreasing or vice versa. Notice, decreasing, increasing, the change occurs, local mean. Increasing, then decreasing, local max. From the change from decreasing to increasing, local mean. This is actually the first derivative test in essence coming up. So one more time. Turning points, where the graph of function changes from increasing to decreasing or vice versa. The number of turning points of a graph of a polynomial function of degree n larger than or equal to 1 is at most n minus 1. So right here, I hope you recognize this. Therefore, 1, 2, 3. This must be one more, so it has to be 4. But anyways, the next one, local maximum point. Highest point or peak in an interval. Function values at these points are called local maximum. Local minimum point, lowest point or value in an interval. Function values at these points are called local minima. Extrema is a plural of extremum, includes all local maxima and minima. So local extrema means both. So maximum, there is one maximum. Minima, we have two of them. So we have one minimum, two minimum. Okay, that's what happens. So how many? 4. Why is that? 1, 2, 3. There are 3 terms. Okay. N minus 1 equals 3. And therefore, 4 should be the answer. Because there are 3 terms. All right. Having said that, we want to find the equation. To find the equation, let's locate the intercepts. This one crosses, this one crosses, this one doesn't, and so we have multiplicity 1 here, multiplicity 2 here. And so again, I'm going to put this arrow, meaning it can't cross, just reminding you of that. And so this is located at, this one, okay. Let me just grab, let's see what color do I want. Okay, this is located at -3, okay. This is obviously -2, okay. And this is located at 1, so it's, in other words, 2 tick marks is 1. Everybody, 2 tick marks is 1. So having said that, so we will have for here x plus 3 times x plus 2 times x minus 1. This one, since the multiplicity is 2 times x minus 1 squared. Now, we don't know what is the leading coefficient. We call it something, for example, a. So f of x is a. This one is x plus 3 times this one is x plus 2 times this one is x minus 1 squared, because the multiplicity is 2. So all we have to do, pick up another point, fairly easy point, and obviously we see the y-intercept located at between 2 and 4, 0, 3. And so you are going to replace the x with 0, f of x or y with 3 to find the missing a. So we have, this is 1, 6a equals 3. So a is 1/2. So f of x is 1/2, parentheses x plus 3, x plus 2, x minus 1 quantity squared, and we are done. It's very straightforward, everybody. I hope everybody's okay with that. Find the degree, leading coefficient, and the maximum number of real zeros of the polynomial f of x is 2 plus 3x to the power of 6 plus 4x to the power of 7 minus 6x. Also describe the end behavior or long run behavior. So again, quickly reminding you of polynomials and how they look like. Polynomial function of degree n in the variable x, p of x equals a sub n, x to the power of n, plus a sub n minus 1, x to the power of n minus 1, all the way to a sub 1x plus a sub 0, where each a sub I is real, a sub n can't be equal to 0, and n is a whole number, 0, 1, 2, 3 to infinity. A sub n is called the leading coefficient. A sub n times x to the power of n is called the leading or dominating term. A sub 0 is called the constant term. First, reminding you of that. So let's put this in descending order first. This comes first, second, third, and last. So this is the descending order. And if we go with descending order, the first term becomes our leading term, 4x to the power of 7. And if 4x to the power of 7 is the leading term, the degree is 7, the leading coefficient is 4. As always, maximum number of real zeros is just the degree, which is 7. And 7 is an odd number, so the end behavior looks like x cubed. So we're going to write leading term for x to the power of 7. N is 7, which is an odd number. That's the key. And a sub n is 4, which is positive, so behaves like x cubed. That means the first and the third quadrant. That is the bottom line. Very straightforward. In other words, as x goes to negative infinity, so does y, or f of x. As x goes to positive infinity, so does y, or f of x. Again, the first and the third quadrants. That's the meaning of it, everybody. Use number of zeros theorem and Descartes' rule of signs to discuss real zeros of f of x. Fill up the table where f of x is 3x to the power of 7 minus 4x to the power of 4 plus 3x cubed plus 2x squared minus x minus 3. So, couple of things. First and foremost, you want to make sure this is in descending order. Yes, it is. Which makes this one the leading term, 3x to the power of 7. And if 3x to the power of 7 is the leading term, n is 7, so the maximum number or the total number of zeros must be 7. So this represents the, positive real zeros, negative real zeros, imaginary zeros, total is 7, regardless. That's what I want everybody to notice. So the total is 7. Now, what about Descartes' rule and positive zeros, negative zeros? Here's the theorem, everybody. Descartes' rule of signs determine the number of positive and negative zeros. How? Let f of x be the polynomial function f of x equals a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 all the way to a sub. In other words, you're dealing with a basic polynomial that has been discussed with terms in descending terms. So that's exactly what we. Then what happens? The number of positive real zeros either equals the number of variations in sign occurring in the coefficients of p of x, or is less than the number of variation by a positive even integer. The number of negative real zeros either equals the number of variation in sign occurring in the coefficients of p of minus x or f of minus x, or is less than the number of variation by a positive even integers. What do we mean by that? Let's pay attention to the concept. So in order to really understand this, I'm going to go back here and I want to emphasize, 3 means positive 3. Negative 4 means negative. So I'm going to write positive, negative, positive, positive, negative, negative. So I'm going to just rewrite the signs. Everybody can see that. There's nothing brand new. This one, and I'm going to read this again because it's important. The number of positive real zeros either equals the number of variation in sign occurring in the coefficient of P of X or is less than the number of variation by a positive integer, a positive even integer. So what happens from here to here, there is a change because it changes sign. From here to here, yes, there is a change. But from here to here, there is no change. Positive, positive. Here to here, there is a change, yes. What about here? No change. Therefore, this is the first one. This is the second one. This is the third change. So, if there are three changes in the sign, how many positive zeros can we have? Three. That's one possibility, everybody. There are other possibilities we're going to discuss, but for now, let's stick with that. And now, what does this one say? It says if you find f of minus x, so the number of negative real zeros either equals the number of variation in the sign occurring in the coefficient of p of minus x, or is less than the number of variation by a positive even integer. So first we want to find f of minus x. How do we find that? Class, you just replace the x with negative x. Anywhere that you see exponent odd, it changes. So this becomes negative 3x to the power of 7. This has even exponent, doesn't change, minus 4x to the power of 4. This becomes minus 3x cubed. This doesn't change, plus 2x squared. This changes to plus x. This doesn't change. Again, I just want to pay attention to the signs. So I'm going to emphasize, I'm going to just write the signs. Obviously, negative, 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 positive. We don't care for the numbers. So what happens? Here to here, no change. To here, no change. From to negative to positive, one change. The number of variation in sign occurring, one change. What about here? No change. What about here? One change. So there are total of two changes, 1 and 2. So negative zeros should be 2. Okay? But remember, what is n? 7. What is the maximum number of zeros? 7. What is the total number of zeros? 7. And by the way, if there is a multiplicity, it counts. Okay? So if I have 3 zeros that are positive, 2 zeros that are negative, the rest of it must be imaginary. 3 plus 2, 5. How many is left? 2. That is fairly easy to follow. Now, if I bring this down, and by the way, imaginary zeros always happen in pairs. In other words, you can't have odd, okay? It can be 2, 4, 10, whatever, in pairs. If this goes down to 1, let's say because it happens like that, or it goes down by an even number. So I have to subtract 2, I get 1. If I subtract 2, I get 0. And if this is 1, this is 0, this must be 6. Again, that's one way. There are other ways to write it, but I want to make a point here. So again, 3, 2, 2 is clear. If we go down by 2, this becomes 1, this is 0, this can't go down anymore, this can't go down anymore either because you have to subtract an even number, and this is. However, I can still have 3 here. So if I have 3 here, this can be 0. If I put 3 here and this goes down to 0, then this must be what? 4. Or I can have this one at 1, this one at 1. This one is still at 2, this is still 4, because the total of 7 should remain unchanged. I hope you look at this table a couple of times to make sure this is understood. What is the least possible degree of this polynomial? 5. Why is that? There are 4 terms, or extremo, or peaks and valleys. What are we talking about? This one is 1. This one is 2. This one is 3. This one is 4. There are 4 terms. Local mean, local max, local mean, local max. Okay. Write an equation for the polynomial graph. Okay. These are the zeros. Crosses, 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 can't cross. Notice it doesn't cross. I'm going to put a double arrow, meaning the multiplicity must be 2. So let's go from left to right. This one, okay, 1, 2, 3, 4 to the left. X, this is minus 4. Let me just make it larger. So minus 4 means x plus 4. Minus 1 means x plus 1. Okay. Positive 2 means x minus 2. Positive 4 means x minus 4. So something like a times x plus 4 times x plus 1 times x minus 2 times x minus 4 squared, because it's has a multiplicity 2. Let me erase my one. Now let's go with an easy number. Obviously, the y-intercept is located at 0, 2, which means I'm going to replace the x with 0, y or f of x with 2, and find the missing a. And this is 16. So we have 16 times negative 2, negative 32 times 4, negative 128. Divide by 2 to get to a, and you get negative 1 over 64. And therefore, the final answer, f of x, is negative 1 over 64 times x plus 4 times x plus 1 times x minus 2 times x minus 4 squared. This is the final answer, everybody.